Hi, Honors Algebra 2 students. Algebra 2 students, we are on lesson 10.4, which is we're going to start at kind of on page 300 of your student journals. We're actually not going to do a ton in your student journals today. We're going to be working mostly with our extra notes packet just to kind of go through some examples. But before we get into that, I do want to talk a little bit about what we're going to be doing today, which is a little bit different. So there's some formulas we're going to add to our formula page if you're doing that. And how this differs from what we have been doing is, right, so far what we have been doing is talking about like independent and dependent events, whether like the probability of A and B happening, or and then sometimes if there was like one depends on the other, that changes our formula a little. Today what we're talking about is something called compound events, and what that means, it's the probability of A or B happening as opposed to the probability of A and B happening. And so it's like, well, you know, what's the probability that it'll rain or that it's a Tuesday? So that's the probability of two things happening. Either one could happen, okay? So it changes our formulas a little, changes our our overall outcome. So the first thing I just want to talk about is what a compound event is. And so in words, it's just the union or intersection of two events. So when we talk about compound events, you know, A or B happening, there can be, like, for example, with my rain in my Tuesday example, there could be a scenario in which it is raining and it's Tuesday. And so that would mean that there is like, you know, so on those scenarios, we would have to maybe like counteract or subtract or account for the fact that if it's raining or Tuesday, what happens if it's both, right? So that's kind of a compound event. Overlapping event is one or more outcomes in common. So again, that's just overlapping. So when two things kind of, like again, in that scenario that I was just mentioning, one or more of the outcomes have in common. And then disjoint or mutually exclusive events means they have no outcomes in common. And so this is just for vocab sense, right? So just to understand kind of like what those words actually mean. Let's talk about some formulas and we'll get into some examples, I think, which would be easier for us to understand. Okay, so for this one, it says if A and B are any two events, then the probability of A or B is, and then it gives you the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So what this means is these events are counted twice. So when it's A and B, we have to subtract out the events or outcomes, if we want to say, that are counted more than once. So I'm just going to say that the events that are counted twice. So that's what that A and B is. So what we're going to do is we're going to figure out the probability of A, and we're going to add it to, this time instead of multiplying, it's going to be adding the probability of B, but then we got to subtract out the times, like basically subtract out the overlap. And then the probability of A or B, if this is a disjoint event, is the probability of A plus the probability of B. So the difference between these two is, one, there's overlap. So in most cases, right, there's going to be an overlap. Like in other words, there could be a scenario in which it's Tuesday and it's raining, so we have to subtract out. We don't want to count it twice, okay? Or in the second one, disjoint events means that there is no overlap. So that's kind of what we're going to be getting at today. There's a couple others. Well, let's go ahead and add this to our page. So if you've been doing a formula page, so far on this formula page, you should have, you know, our independent, our dependent, right? So our independent and our dependent formulas. And now what we're going to add are our compound events. So let's just write, I'm just going to write compound events. And then I'm going to do the two formulas. So it's the probability of A or B equals the probability of A plus the probability of B, and then you're going to subtract out the overlap. So minus the probability of A and B. And again, this is kind of, I just want to mention that this is the overlap. And then for disjoint events, if there is no overlap, then it's just basically the probability of A plus the probability of B. And you wouldn't have to subtract out any overlap because, well, there is none. Okay, so let's chat a little bit about, let's do some of the formulas or some of the problems in our extra packet, right? This is our extra notes packet, the one with all the examples in it. So let's kind of start there. So on the first one, it says 2 6-sided dice are rolled. What is the probability that the sum of the numbers rolled is a multiple of 4 or is 5? So this is how you can tell this is different than an independent-dependent event because we're saying the word or in here. So you do want to pay attention to that word. If it asks for the, the sum of the numbers rolled is a multiple of 4 and is 5, then that would change our scenario some. So what I did first is I just kind of like listed out all of the possibilities when it came to rolling a 6-sided dice. Now we use this one kind of a lot. So I'm just going to go ahead and, if we could get a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, and a 1 and a 6. And so I'm just going to list them all out, which seems a little tedious, but I think in some cases it helps to kind of see them all, listed out. So when it's not too bad, like this one, I don't find it to be too outrageous to kind of write them all out. I like to see all of my outcomes. And again, this is just called your sample space. So let me just kind of put all these in here. And so that way I make it easier to kind of think about all of our favorable choices here. Okay, 6 1, 6 2. All right, so those are all the outcomes in our sample space. So there's 36 of them because there's 6 for each column, and then there are 6 columns. So 6 times 6 is 36. So what we want to figure out is the probability of A or B. Okay, so that's kind of our game plan. So the probability of A or B happening, which means we have to decide if there's any overlap. So are these disjoint events? So in other words, do they have overlap or do they not? So can the sum of the numbers rolled is a multiple of 4 or is 5? So the probability that the sum of the numbers rolled is a multiple of 4 or is 5. So is there any overlap here? Can the numbers rolled, can the sum of the numbers be 5, but also be a multiple of 4? And the answer is no, they can't, right? So there's no overlap here. The probability that the sum is a multiple of 4 or is 5, the sum is 5 means that 5 in and of itself is not a multiple of 4. And so therefore there is no overlap here. So the formula we're going to use is the one that has no overlap, which is the probability of A plus the probability of B. So then what we're going to do is we're going to look at our first scenario. So let's let A be the first part. So the sum of the numbers rolled is a multiple of 4. So we're going to call that A, and then the sum is 5 would be our B scenario. So what I'm going to do is I'm going to say, okay, probability of A or B, or you could write out the words there if you wanted. The sum of the numbers rolled is a multiple of 4 or 5. Probability of A happening. How many of these scenarios gives us a multiple of 4? So let's think about first of all, what a multiple of 4 is. So it means like 4 times 1 is 4, 4 times 2 is 8, 16, 4 times 3 is 12. Any of those numbers would give us a multiple of 4. So multiples of 4, are kind of listed there. So 4, 8, 12, 16, 20, 24, and so forth. So let's circle all the ones where the sum of these two numbers is one of those multiples. So here's 4. Here's 4. Let's do all the 4s. Here's 4. Okay, let's find 8. Well, we don't have 8 there. Here's 8. Here's 8. Here's 8. Here's 8. Here's 8. Let's see if we can get 16. Can the sum of the numbers be 16? And the answer is, well, no. I'm sorry, I skipped 12. Let's see, can we do 12? We got 9, 10, 11. Well, it looks like we can get 6 and 6 as a sum of 12, which would be a multiple of 4. I think that's it. So let's think about how many of these give us a multiple of 4. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So our probability for A is 9 out of 36, because there's 36 total outcomes, and 9 of which give us a sum that is a multiple of 4. Now let's go through and figure out which ones give us a sum of 5. So 4 and 1 gives me a sum of 5. 3 and 2, 3 and 2, 4 and 1. I think that's it. So in this one, I would say the probability of B happening, so plus, is 4 out of 36, which makes the probability of A or B happening. So the probability that you can get a multiple of 4 or that the sum is 5 would be 13 out of 36. And you can leave that right as a fraction if you want, or if you want to write it as a percent. To be honest with you, I think most of the time they're going to leave this as a fraction. And just reduce the fraction if you can. In this case, it can't be reduced. All right, let's take a look at some other examples. So number 2. A bag contains cards numbered 1 through 20. One card is randomly selected. What is the probability that the number on the card is a multiple of 3 or a multiple of 4? So a multiple of 3 or a multiple of 4. So if you think about what multiples are, right? So multiples of 3 are 3 times 2 is 6. So 3, 6, 9, 12, 15, 18, and so forth, right? And multiples of 4 are 4, 8, 12, 16, 20, 24, and so forth. So can a number be a multiple of both things? And the answer is yes, because I mean, you can even see it in just the ones I wrote out that they both have a 12 in it. So this definitely is a disjoint event, which means, I'm sorry, this is not a disjoint event. This means that there is some overlap. So the formula we're going to use here is the probability of A or B, but we're going to do the probability of A plus the probability of B minus the overlap, which is A and B. Okay? So that's our formula we're going to use. So let's think about what we're going to, kind of the probability of getting a multiple of 3. So I'm going to go back to my, so a bag contains numbers 1 through 20. One of the cards is randomly selected. What's the probability that the number on the card is a multiple of 3? So out of 1 and 20, I guess we can cross off 24 here. I would have 1, 2, 3, 4, 5, 6 times. So I would have 6 times out of 20 that I would get a multiple of 3. So a multiple of 4 out of 20 would be 1, 2, 3, 4, 5 times. And then out of 20, so if 20 is the max, how many times do we overlap? Well, I know we overlap here. Do we see any other overlaps? I don't see any. So in this case, I would have to subtract 1 out of 20. So this is going to be my formula, what I would use to figure out the probability of A or B happening. So this would be 11 minus 1, which is 10 out of 20, which is going to give me 1/2. So again, that's an example of one where there is an overlap. All right, number 3. Out of 45 customers at a breakfast cafe, 42 customers bought either coffee or orange juice, and there were 30 customers who bought orange juice and 40 customers who bought coffee. What is the probability that a randomly selected customer bought both coffee and orange juice? Okay, so think about what you're finding here. You're actually finding where both things happen. So you want to know when both things happen. So there is overlap here because there's situations, they already kind of told us there are people that would bought both. So if we're going to label our scenarios, like probability of A, I would say is the probability of getting coffee. And the probability of B will represent the probability of getting orange juice. So those are two separate events, right? Probability of coffee, probability of orange juice. Then we have the probability of coffee or orange juice. And then we have the probability of both. So this is the probability of coffee and orange juice. So there is overlap on that. So what we're going to do is we're going to still use our same formula, but the one with overlap. But this time, instead of solving for, solving for the probability of A or B, what we're actually going to do is we're going to solve for the probability of A and B. And the reason why is because it says out of 45 customers, so this is our total, 42 customers bought either coffee or orange juice. So what they're telling us here is that 42 customers are in the or category. So this would be 42 out of 45. There were 30 customers who bought orange juice, so 30 out of 45, and 40 customers who bought coffee, so 40 out of 45. And so now what we're going to do is the only thing we don't know is this A, and so that's what we're actually going to solve for. So let's plug everything back into our equation. Let's see what we can come up with. So in this one, I'm going to plug in A or B, so that's 42 out of 45 equals the probability of A, which is 40 out of 45, plus the probability of B, which is 30 out of 45, minus the probability of, minus the probability of A and B, which is what we're actually solving for. So that's what we're actually solving for. All right, so what I'm going to do is I'm going to go ahead and solve this like I would a normal algebra equation. So I'm going to go ahead and combine some like terms. So I'm going to add those together. Think of this as like an x, right? You're just solving for x, except we're solving for a probability. So let's subtract both sides. So I get negative, let's see here, I get negative 28. And then I'm going to divide both sides by negative, because that doesn't really make sense to have a negative probability. And so my final answer asks for, what is the probability that a randomly selected customer bought coffee and orange juice? So I got 28 out of 45. And again, this is a scenario where maybe the percent would make a little bit more sense. So it's about 0.62 or 62%. So 62% of the time, a randomly selected customer bought both coffee and orange juice. And so that's kind of how you would use that formula in a little bit different scenario. All right, so this is another formula I'm having us add to our list here. And so what this is all about using more than one probability rule. So what we're doing here is we're talking about like the probability of B equals the probability of both things happening, plus the probability of not A happening, but B happening. So again, these are just kind of random, like specific examples. This is the probability of B happening equals the probability of A times the probability of B given A, plus the probability of not A happening times the probability of B not A happening. Okay, so none of that makes a whole lot of sense, right? But let's look at an example in which we would use this. So again, this is partly why I don't make you memorize these formulas, because I find them to be very confusing. But also, it's not, I mean, if you had to use this in real life, you would probably look this up. All right, so let's look at a scenario. A medical association estimates that 10.9% of the people in the United States have a thyroid disorder. Suppose a medical lab has developed a simple diagnostic test that is 96% accurate for the people who have the disorder and 99% accurate for the people who do not have it. The medical lab gives the test to a randomly selected person. What is the probability that that diagnosis is correct? So this is a specific example. And so what I'll tell you on this one is kind of where, number one, we're using formulas, but also that we're going to be, like this is an example in which we're going to use like more than one of these probability rules that we've already talked about. So let's kind of look at what we have so far. So the Medical Association estimates that 10.9% of people in the United States have a thyroid disorder. So we'll say the probability of A is 10.9%. I'm going to write that as a decimal. So it's 0.109. And this represents the thyroid disorder. Okay. Then we also have these, it says, suppose a medical lab has discovered that a simple diagnostic test is 96% accurate for people who have the disorder and 99% for people who do not have it. So what we want to figure out here is, because we're about people who have it and don't have it. We want to figure out the probability of not having a thyroid disorder. So all you're really doing there is taking 100% and subtracting 10.9%. So if you do that, you get about 89.1% or 0.891. So what this is meaning is that this is the percent or probability of people who do not have a thyroid disorder. So they didn't specifically give us this number, but we could figure it out based off of the fact that we know how many people do have that disorder. All right, so probability of B. So let's think about what B would represent. So suppose a medical lab has developed a simple diagnostic test that is 96% accurate. So what we're trying to figure out, and then it says for people who have the disorder and 99% accurate for people who do not have it. So it's dependent on people who either have it or don't have it. So what we're looking at there is if B represents kind of having the correct diagnosis or correct diagnostic test, right? So if we have a diagnostic test, if it's accurate, 96% of the people who have the disorder, 99% of the people who do not have it. So then what they're giving us here is the probability that B happens given A has occurred, and the probability of B happens given not A has occurred. So in other words, they're saying, okay, 96% accurate for people who have a thyroid disease, so given A, so people who have a thyroid disorder, it is a correct diagnostic test given that you have the thyroid disorder. So that's a 96% accuracy rate. So what they're giving us here is the probability of B given A. The second part says it's a 99% accurate for people who do not have it. So not A, which is the people who don't have the thyroid disorder. So if that occurs, then the diagnostic test, which is B, is 99% accurate. So what they're giving us here is kind of all of this little bit of information. So they're telling us thyroid disease and then not thyroid disease, correct diagnosis, and then the probability of B given A, so the probability of having a correct diagnosis or a diagnostic test given that A has happened, and then a correct diagnostic test given that not A has happened. All right, so taking a look at our scenario here, we're going to use our formula that involves the not B and the not A, because that's what we were provided. So we're going to use the probability of B equals the probability of A times the probability of B given A plus the probability of not A times the probability of B given not A. So again, because in this particular scenario, we were given these two kind of pieces of information, then we're going to use the second example. All right, let's plug in our numbers where they belong. So I'm going to get probability of B. So we're looking at what is the probability that the diagnosis is correct. So this is a correct diagnosis. That's what we're solving for. So probability of A is 0.09 times the probability of B not A, which is 0.96, plus the probability of not A happening, which is 0.891, times the probability of B not A happening, which is 0.99. So again, this is just a little bit confusing, obviously, just because there's a lot of things going on in this problem. But again, this is multiplication, then you're adding those two things together. All right, so I'm going to put this in my calculator. I get about 0.10464, just kind of give me a few decimal places here. And then on this one, I got 0.88209. Put those together, I get about 0.98673. So what does this tell us? What is the probability that the diagnosis is correct? Well, it is correct approximately 98.7% of the time the diagnosis is correct. So that's what that's given us. So this is what we're doing here is a very specific example given the information that we're providing. So like, for example, if we're given this information, how we would kind of put that together to figure out a probability. There isn't a specific, one of the rules that we've done prior to this didn't exactly fit into that. So this is kind of combining a couple of the probability rules that we talked about previously. Okay, I would practice some of this stuff. Again, it gets a little confusing, so I know that. So practice some of this stuff, and then we'll do some more in class. And then if you have any questions, we'll talk about that as well. All right, that's it for now. Bye.